This is Seung and I'm the director of Sky Academy, and in this particular episode I'm going to be basically summing up the whole of calculus differentiation. You would have now watched all the videos, yeah, and so you're familiar with everything. I've just made this particular episode to wrap things up, to bring things all together, just so that you are aware of what we've just learnt in this particular chapter. So let's begin. So we started off looking at limits. Yeah, what is a limit? Okay, a limit is basically the value that a particular function approaches, right, which may or may not necessarily be what that particular function is equal to as it approaches a certain value. Okay, so for example, in a particular function, the limit of that function as x approaches to c is the value that that particular function approaches as x does approach c. Now, oftentimes, for most functions, the value of a function at c will be equal to the value of the function as x approaches c. Where this may or may not be the case is particularly where the function doesn't exist at c, because if you substitute x is equal to c into a particular function, the denominator might become 0, yeah? So because you can't divide by 0, right? If a particular function, the denominator of a particular function approaches 0, right, then the function breaks down at that point, but that's not necessarily to say that the limit of x as it approaches c will break down either. The limit might exist, although the function might not exist, yeah? So that's often where we use this particular limit as x approaches c. The other limit that we looked at was as x approaches positive or negative infinity, right? Or as x approaches a positive or negative value that's infinitely large. Yeah, and we looked at what happens there. Yeah, and oftentimes, I mean, a good place to look at is rectangular hyperbole, right? So when you look at a rectangular hyperbola, basically it'll just extend forever to the right and to the left, and you want to actually examine what happens there. Does it approach a specific value, like does it approach the x-axis, or does it shoot off into infinity itself? So that's really oftentimes worth examining the limit of a function as it approaches positive and negative infinitely large values. The next thing we looked at was continuity, and by continuity what we're looking for specifically is that the function continues on. Now, you can pretty much tell when a function is continuing on, or whether there's a break in the continuity of that function. When we examine it, you can pretty much tell. However, from a mathematical point of view, right, for there to be continuity, for you to test continuity, right, what we're looking for is not just that the pen, so that when you're graphing the function, the pen doesn't leave the page. What we're actually testing for there is a much more mathematical test, and that basically is that the limit approaching the function in one direction and the limit approaching the function in another direction is equal to the exact value of the function at that specific value. Does that make sense? So basically, the function approaching from the left and the function approaching from the right is going to meet, right, at the exact value of the function, and that is your test for continuity. After the test for continuity, basically we looked at limits, continuity, and then the next thing we did was look at really what differentiation was about. Now, we looked at differentiation by first principles. Now, what is differentiation? Differentiation is specifically looking at rates of change. Now, what we mean by a rate of change is the gradient of a particular function, all right? So we know how to find the gradient of a line. We know how to find the gradient between 2 points, yeah? And the gradient between 2 points is m, which is your gradient, is equal to y2 minus y1 over x2 minus x1. In other words, it's your change in y over your change in x. Another way to say that is rise over run. Yeah, it's your change in your rise over your change in your run. Okay, between 2 points, x1, y1 is your first point, x2, y2 is your second point. So that's basically how you find the gradient between 2 points. But when it comes to differentiation, we're not only interested in the gradient between 2 points. Remember, for differentiation, we're actually interested in the gradient not just at 2 points, but at one specific instant. Yeah? So what we need to do is we need to find the gradient between 2 points and slide that second point all the way to the point where it meets the first point. Yeah? So that's really what differentiation is about. And basically when we do that, we can find the gradient of a curve or the tangent of a curve at an instantaneous point on that curve. And that's really what differentiation by first principles is. And we basically did that by using this formula here, which is y2 minus y1 over x2 minus x1. And what we ended up with is that the gradient, in other words, what we write here is the derivative, right? F dash of x, and that's basically what the derivative is f dash of x, all right? The instantaneous gradient at that particular point is given by f of x plus h minus f of x all over h as h approaches 0, the limit of h approaching 0. And remember, the limit of h approaching 0 is basically the gap between those 2 points becoming 0. Does that make sense? Right, so that's what we did. We looked at differentiation by first principles. I looked at an example of how to apply it. But then what we did was we looked at and we looked for shortcuts in how to differentiate. Shortcuts in how to find the derivative, and we came up with a rule which does all the hard work of differentiation by first principles for you. And that rule is basically what I've got here, differentiation by rule. And the rule is this, right? If you've got a function, right, which is a times x to the power of n, so for any general polynomial, what we do is we take the power of n, multiply it by the coefficient, so in other words, multiply by the power, and take 1 off the power to give you a new power, okay? So you multiply by the power and take 1 off the power, yep. Okay. We then looked at how to apply that to different polynomial type equations, all right? Or polynomial type functions, but we also looked at how to apply that to functions where you've got negative indices, right? So 1 over x to the power of n is basically the same as x to the power of negative n, and you can apply this rule to negative powers, but we also learned to apply this rule to fractional powers, right? So in other words, indices where your indice is a fraction, yeah? And basically what you've got here is that when you've got x to the power of a fraction, right, you've basically got the root to the power of the denominator of x to the power of the numerator, yeah? And if it's negative, it's 1 over that, yeah? Cool. So we learnt to apply the differentiation by rule to negative and fractional indices. We then kind of had a look at the different notations for what differentiation or the derivative are, right? So we looked at, like for example, that is the derivative, f dash of x. So expressing the derivative by the way, just really means the rate of change or the gradient function of a particular curve. And we got that as being dy dx, right? That's, in other words, the change in y over the change in x, right? Incremental changes, only tiny changes of y over tiny changes of x. F dash of x, x with a little dot on top, which is the Newtonian form of expressing derivative, y dash of x, right? Y dash as a particular function as well. We then looked at three particular rules that are of importance to us. We looked at the function of a function rule, or the chain rule. Go back and have a look at examples of that. We looked at the product rule, right? And we looked at the quotient rule, yeah? And I've got them on the board. The examples that I go through will help you to apply that. And I will warn you here, sometimes with doing questions like this, it can get to the point where you're using both the chain rule and the product rule together. You can also be having functions where you use the product rule and the quotient rule together. Like it gets to the point where when you get really good at this stuff, there's all sorts of ways that they can get you to apply the chain rule, the product rule, and the quotient rule in a particular question. So be mindful of that as we go through it. The final thing that we looked at is the whole idea of primitives or antiderivatives. Now, what is a primitive or an antiderivative? It is basically the reverse process, or the opposite of differentiation, right? So what's the opposite of plus? It's minus. What's the opposite of multiplication? It's division. Well, what's the opposite of differentiating a function? It's finding its antiderivative, or in other words, finding its primitive, yeah? And we basically express the derivative, or the primitive, sorry, not the derivative, as capital F of x, right? So if you've got the function being f of x, the primitive will be capital F of x. Now, what you also find is that when you do find the primitive, or when you do anti-differentiate a function, what we do is, instead of taking one off the power, we add one to the power, and instead of multiplying by the old power, we divide by the new power. Okay, so let me just say that again. Instead of taking one off the power, you add one to the power. Instead of dividing by the instead of multiplying by the old power, when you find the antiderivative, you divide by the new power. So basically what you're doing is a times x to the power of n becomes a times x to the power of n plus 1 all over n plus 1, which is your new power, yeah? So that is a really a good summary of the chapter on differentiation, yeah, on calculus, the introduction to calculus. I'm going to stand to the side now so that you can take that all in. But thank you very much for watching. I look forward to seeing you on the next chapter, which is all about geometric applications of calculus, right? So applying calculus to curve sketching, to graphs, etc. Okay, thanks again. Bye.